All right, we're in the last section of chapter 9, 9.6, non-ideal gas behavior. So here we're going to describe the physical factors that lead to deviations from ideal gas behavior, explain how these factors are represented in the van der Waals equation, define compressibility, or Z, and describe how its variation with pressure reflects the non-ideal behavior, and quantify non-ideal behavior by comparing computations of gas properties using the ideal gas law and the van der Waals equation. So in real life, gases aren't ideal. So our good old Pivnert equation may really not be accurate. One way that we judge the accuracy of Pivnert is by using the compressibility factor, which is the ratio of the actual volume of one gas, so molar volume, to the volume of 1 mole of an ideal gas at the same temperature and pressure. So this ends up being equal to P times that molar volume divided by RT, and this is measured. The ideal gas, if it's an ideal gas, the ratio is 1. The further from 1 that you are, either lower or higher, the less ideal your gas is behaving. When we go to high pressures, the ideal gas law really does not describe it well. It's because our molecules with that high pressure are closer together and really can't be as compressed. So there's less space. And even though volume and pressure are decreasing together, they're not doing it proportional to Boyle's law. So Boyle's law even is falling apart. So at lower pressures, though, there's a lot less attraction to each other because there's not much compression going on there. So because of this, they can act more like an ideal gas. And you can see that with this plot here. As we get higher in pressure, we see that Z factor getting rapidly higher and higher for all these gases. Whereas when our pressure is lower, yeah, we get to, some areas, some of these really low pressures where we have a non-ideal ratio, but it's a lot closer to 1 overall at the lower pressures than it is at the higher pressures for these different gases. So here we're showing a difference between ideal versus real gases. So an ideal gas, they aren't attracted to each other. They're all behaving independently. But in reality, there are some attractive forces happening. So the real gases are somewhat attracted to each other, and because of this, they're a little closer to each other, which would decrease the volume. And then in B, what's happening is, the ideal gas, they hit the side of their container, bounce off, do their own thing. But with the real gas, the attractive forces that are happening between the gases are going to decrease the force of the collisions between the molecules and the containers of the wall. So there's less pressure exerted compared to an ideal gas. So we actually have terms to account for the volume of gases and attractive forces. So we add these terms to PV equals nRT, and this is called the van der Waals equation. So to correct for pressure, we take our ideal gas pressure and add AN squared over V squared. So A corresponds to the strength of the attraction between molecules of a gas. This term itself is a lot more important at low pressures. And then B, that should be a lowercase b. Okay, it goes with our volume term, so V minus NB, so N being the number of molecules. This is a lot more important at high pressures and small volumes. And table 9.3 in your book gives you some values of A and B. So these van der Waals constants for some common gases. So bookmark this. I would highly recommend you bookmark this table. So that way on your exam you can go back and have these values if you need them. So we're going to look at an example. A 4.25 liter flask has 3.46 moles of carbon dioxide at 220 degrees Celsius. Calculate this pressure of the sample, A, from the ideal gas law, B, from the van der Waals equation, and C, explain the reasons for this difference. So from the ideal gas law, from PV equals nRT, Okay, solving for pressure, we get 33.5 atms. So we went and changed our degrees Celsius to Kelvin, so it's 502 Kelvin. We already had a volume. We knew our moles, and then we're using our 0.08206 value of R. Now, if we use the van der Waals equation here, okay, we know we're solving for pressure first. So doing lots of doctoring this up, we get that our pressure is equal to nRT over V minus NB minus N squared A over V squared. So we know our N, we know R, we know T, we know our volume, we know our N again. B we get from the table, so this is CO2, so look at the table for B, look at the table for A. Plug everything in, and you get a pressure of 32.4 atm. It's actually pretty close to the ideal gas law. And that's because our pressure really isn't that high. Okay, to me it seems pretty high, but overall, for what we're talking about here, this isn't super high pressure, and the temperature isn't that low either. Okay, the reason that there's some difference though is because there are some volume differences due to the attractions between the molecules. And the gas law assumes they don't have volume or attractions, but we do. So that's what accounts for that difference. And that does it for Chapter 9. Hopefully you guys are doing well, studying up. And as usual, if you have any questions, let me know.